So that's the story that I'm going to tell. It'll be partially on lead perovskites, and the second half will be some unpublished work on copper perovskitoids. The story, my story with this really began in the fall of '96 when I was randomly assigned a task in Ken's lab, and I never really left. You know, all of these decades later, here we are. So I just wanted to congratulate Ken on the symposium and thank him for literally decades of support and mentorship, which I very much appreciated and affected my career quite a lot. And metal halide perovskites are well known to a lot of us. They have some potential in a wide range of applications. My focus on these compounds have effectively nothing to do with the application. Instead, I take a much more fundamental approach to it. My interest is how do we think about this really diverse set of compounds with different A and B cations and halides? How do we think about the synthesis of these in order to control structure, or at least understand how the many different variables present in these materials affect the resulting structures and compositions? And how do we access them synthetically? Ken alluded to some of this work that I did, several years ago. An approach that we've taken in my lab is to try to use some data science techniques and machine learning techniques to augment our understanding of the right? So machine learning is not a silver bullet that's going to tell us the answer, but it can reveal some trends and some things that are hard for humans to see, right? Humans are very good at seeing some patterns and very poor at seeing other patterns. And a typical approach that we employ is to try to get a database of reactions, calculate some descriptors of the reactants and the reaction conditions, use different sorts of techniques in order to generate some model from which ideally we can construct some testable hypotheses, which we then test and feed into the next round. We let them go through this process a few times, and every time we do that, it enhances our understanding of the system. The work that was published, and this is all based on oxide, and so it was a lot of the thermal oxide work that I've done for a long time. In these initial experiments, we digitized like a dozen years of experiments. To do any of this sort of thing, it requires experiments, it requires data. If you want to model or try to understand the synthesis, we need access to synthetic data. But of course, there are no great repositories in the literature of synthetic data. What you see in the literature is the experiments that have worked, the things that don't work, but of course don't get communicated. And the successful reactions that do get communicated are formatted widely and very diversely into the chapters. When we wanted to change systems from oxides to halides, we acknowledged that we didn't have any of the data that we were going to need in order to do any machine learning. So our approach was to not try to extract a lot of information from the literature, but to do a lot of experiments. And the approach that we took to do that was to use liquid handlers to do a lot of our experiments. We used high throughput techniques, sort of semi-automated platforms in order to generate a lot of experimental details. Humans and robots are good at mutually exclusive things, right? We can do whatever we want. Reactions can be as complex as we absolutely want. I can start a reaction on one side of the lab and cross the lab. I can cross the building. I can cross the street with a reaction. Robots can't do any of that. Humans are not particularly fast. They're not particularly accurate. Precisely, we keep horrible records. Robots are just the opposite. What they can do is very limited, but they are very precise and very accurate if you're asking them to do things that they're capable of doing. And they keep meticulous records in the form of log files, so we know exactly what happened, when it happened, in a readable fashion. And so in a workflow like this, we use humans for the things that humans are best at and robots for generating a lot of experimental details. The idea is human intuition defines what we do. A lot of the tedious file generation and calculations are done using the automated platform. We do lots of reactions. Data visualization is then much more straightforward because we're spitting out well-normalized data sets, which are ideally suited toward machine learning type techniques. When we do this, we have to be careful in that a lot of our reactions are robotic reactions, but we also do human-controlled reactions. We need a way in which to describe these in a similar sort of fashion, right? So what I've got here is just one of my students' lab notebooks, which is kind of a standard looking lab notebook. We had to develop an ontology for an experiment such that we could translate this into something that would make sense in a database. And so it's things like, who did the reaction? What was the purpose of the reaction? How do we describe the reagents that we're using in a unique fashion? What were the actions that were performed on the reactions? What's our observational information? And what outcomes might we be trying to model? And so we wanted to do this so that the data that we would get from the human controlled reactions, the robotic reactions could fit into this sort of database. In order to make this easier, we developed what we call Escalate, which is really just it's an API, or there's an API for it. It is a data pipeline. So it is designed to do a lot of the tedious calculations. If we're doing lots of reactions, we don't want to do a lot of the calculations required to figure out exactly what we need to do. And so Escalate will do things like define the state space in which we can work, if we can figure out the concentrations of our reagents. It will help us, if we want to do a grid search, we want to do some random, so we can generate reaction points. We can generate the input files that our robotic platforms need in an automatic fashion. Once we've done our reactions, it can ingest the output files along with associated some passive metadata, like lab atmospheric type information. And automatically it can add an interpretive layer, some calculated descriptors of the reactants, the reagents, things like that. And it helps with data reporting and the generation of nice, well-normalized data sets. And so we use this to avoid a lot of the tedious things that one would have to do by doing lots and lots of experiments. And so in the context of lead halide perovskites, the first workflow that we chose to look at, so all of the initial experiments and for the next 5 or 6 minutes will all be on lead. And we started with inverse temperature crystallization. And so this is the approach where you're doing reactions. Crystallization happens at high temperature. As the temperature decreases, the solubility increases. And so temperature management is an issue. And so, we would select our reagents. This is what the robot deck looks like. And so we have our different solutions. We're doing them in 96 well plates. And so we would do 96 experiments at a time. It took about 5 hours in order to 5 hours of robot deck time to do 96 experiments. So it was pretty good. We looked at a lot of different chemical systems and did thousands of experiments. We discovered ITC behavior in a lot of materials. There's a bunch of things that we need to worry about, though, of course. If you're generating a lot of reactions, we could just be shifting the choke point somewhere else, right? If our characterization or the observational information is still manual, we're just taking a choke point from the experiment and shifting it somewhere else. So we have to be mindful of that. We worry about temperature modeling and things like that. This is some of the crystal imaging and that we would use to characterize our materials. A nice thing about the way in which we ingest our data is that we can generate plots of in concentration space, the outcome of experiments, and visualize where experiments are working and where they're not working. Some systems like this ethyl ammonium have a lot more points than others, and we can use that to better understand the regions in which we're seeing successful reactions. The experiment convex hull is just the concentration window in which we can work. We can visualize the volume of that, which is dependent upon the solubility of our stock solutions. And then, of course, the convex hull, where we actually see success, and it varies quite a lot. There are some systems like formidinium where the concentration windows are small, but the success of reaction is quite high, and then others where, for example, like pyrazine, where the concentration window, the experiment convex hull is quite big, but it's very little success. A machine learning work on these data within a given system work pretty well. So we could do an interpolation was really successful in the model that we built, could predict the outcome of the experience quite well. But extrapolation between systems was much more of a challenge, and that was certainly much more difficult. But we wanted to expand this to see if we could add additional synthetic workflows. And so the next wave route that we took was anti-vapor diffusion, where we have a mother liquor with all of our solutes, and so anti-solvent typically dichloromethane. Dichloromethane by vapor pressure diffused into the mother liquor changes the solvent properties, gradually inducing crystallization. We get a concentration gradient of the anti-solvent across our variable or across the vial. Here, it takes about an hour to run 24 reactions, and so I'll show you a photo of this in a couple of slides, what the custom block that we designed actually looks like. It only takes about an hour of robot time, but then it takes 24 hours of that time to allow for the diffusion to occur. And with this, this approach is a little bit more generalizable. We looked at a lot of mixed halide systems, mixed A-cation systems. We were able to access a wide range of new phases and make a bunch of new materials. A challenge with a lot of these halide perovskite instabilities, another approach that we took was to set up a mechanism by which we could do some longitudinal study. So we designed and built 3 different environmental chambers where we can do longitudinal studies, where we can control the temperature, the light level, and the humidity independently, taking continuous or nearly continuous optical images of many different samples at once, and using the optical images of the proxy for stability, we could extract degradation kinetics from those sorts of things. Our setup was designed around bulk samples, but then there was another setup designed around thin films and full devices. When we look at this, and here are some data for methyl ammonium lead iodide, we can, from the optical images for each of our different samples, we can extract RGB values, and they correlate to they correlate to structural changes within our system, which we could measure in using ex situ or so this was all lead work, and we looked at a couple of different workflows. We looked at different halides, many different A-cations. We wanted to see if we could extend our robot-ready perovskite approach to other B-cations as well. And so the next set of cations that we wanted to look at was copper 2+ systems. It avoids a lot of the toxicity issues. Again, our focus is not on property optimization, and so these copper materials are not particularly good in terms of their photovoltaic efficiency, but that's okay. We're more interested in the fundamental formation principles that govern all of these sorts of materials. When we began this, the chemical space was largely unexplored. We see a range of inorganic dimensionalities for the materials that we can produce. Here are a few of the compounds that we have formed. Every time we change things, there's a fair amount of reoptimization that's required. Going from what we see in the literature to robot-friendly syntheses is not a trivial task, and it takes some time. And so when we shifted from lead to copper, we sort of defined an experimental. And the way that we look at it is sort of like this, right? So we see what's in the literature. The syntheses of the materials in the literature are very diverse, created under a wide range of conditions. We need to see what of those compounds, which of those we can access using our robot-friendly techniques. So we're using a liquid handler. So that means that we have to use liquid only, no solids. That's considered slower. And we can't use any strong acids, which are common in a lot of these things, because that would degrade the robot in an expensive way that I don't want to deal with. So once we do a little bit of that, a little bit of adaptation, we then end up with sort of a robot-friendly database compound. At this point, we do some system selection. The liquid handler that we use can accommodate different liquid viscosities, but there are ranges of what it can and cannot do. And so there are some compatibility tests that we also worry about. We worry about concentration limits, because the concentrations of the solutes in our solutions dictate the size of the concentration space in which we can work. We then run our experiments. We characterize the material that we get, mostly with powder active diffraction. We find new materials and we use crystal active diffraction in order to do a lot of the structural work. And at this point, we have sort of an enhanced database of compounds. And this is where we either use our own chemical intuition to try to generate some testable hypotheses, or we augment that with some machine learning techniques. The story that I'm going to tell you about in the next 5 or 6 minutes will be essentially one group around this, coming up with some testable hypotheses. Again, anti-solvent vapor diffusion, right? So our initial experiments sort of look like this. It's a vial in a vial with the mother liquor on the inside and the anti-solvent on the outside. We allow the diffusion to last and to go for maybe 18 and 24 hours. If we're doing it on the robot deck, this is like an excised version of what our block looks like. where we have individual vials for the anti-solvent, and for the mother liquor, crystallization tends to occur at the top where the concentration of the anti-solvent is greatest, inducing crystallization. Solvent systems that we look at, a lot of GDL seems to work the best. DMF and DMSO are less appropriate solvents in that the products are too soluble and it's harder to achieve the critical concentrations required for nucleation and crystallization. No temperature control is required in this system, which is nice with respect to a lot of the ITC work. This is my robot, or the robot deck as it looks when we actually run our experiments. For these reactions, because it's a liquid handling, we've got 3 liquids, neat solvent, the copper chloride in GBL, and the copper chloride and the ammonium halide in GBL. The stock solution concentration varies pretty widely by system. This is the block that we designed. It's really based upon a 96 well plate. We just removed half of the vial, half of the wells, which enable us to isolate each 2 well reaction chambers separately from one another. So we have a 48 well, 24 reaction chambers, so we can do 24 reactions in one shot. Again, it takes about an hour or so to fill these, for the robot to fill this, and then we can allow these to sit on the robot deck, and so we can run many of these in parallel. A cation choice. So for
Can you go back to that slide?
yeah,
Usually in this design, there's a cover on that,
there will be a cover.
and but each cover has a little hole in them. Yeah, I mean, you only have two of them.
So there is a recess cut in between here. And so the cover that we screw down, the seal here is sufficient to isolate these 2 chambers from one another.
But if you have to redesign that,
Well, we designed the whole thing. I mean, we redesigned this CAD, and then there are a lot of cloud-based machinists. You just send them a CAD file, and 2 days later you get your log, and it works pretty well. So so these are the 8 cations that we use. It's all 1+ cation, structurally diverse. They're pretty big, so we're expecting lower dimensionality compounds. And this is sort of at the point where we could start doing our reactions. And this brings me back to the earlier part of the story, right? So the way in which we chose to explore these is reminiscent of some old work. So this is my second paper from Ken's lab on cadmium oxide, niobium oxide, HF pyridine, and water. And so this is the second paper that I published. It's probably good that Shiv is not here. We misspelled his name in this, right? So we actually shortened him in A. So if I had to guess, I would say it's 85% chance that it's me. And maybe, he was gone by that. It was probably my fault. Kevin Meyer probably took the blame, but it was probably mine. But he's not here to say, right? I mean, I don't think he's worried about his agent deaths. I don't think that this paper is going to kill him. I think he'll be okay. For our system, this is what it looks like. Instead of mole fraction, plotting the outcome of the experiment as a function of mole fraction, we plot the outcome of the experiment as a function of the concentration of either the ammonium cation or copper chloride, and then we can see that certain types of compounds dominate the crystallization in different regions, and of course, the concentrations of our corners define the concentration of space in which we can work. So we want to push them out as far as we can. For the reaction, we would
take that there,
indeed, absolutely we could. So we would do at least 41 reactions per system. The first 24 would be random, right? So random explorations is a pretty efficient way to do things. We would also have 17 targeted experiments, which would ensure that we would have good coverage under high copper chloride concentrations, which is where we tend to see the perovskites form. And we would see things that look like that. If we look at the 5 systems in total, these are what they look like. And so here are our 5 different systems. You can see that the points of the solution concentrations move. This is a little bit higher, that's a little bit lower. These just come from the inherent solubility limits in our different systems. But there are certainly some commonalities. We see a few big classes of material. We see some perovskitoids, 2-dimensional perovskitoids, copper chlorides. We see what I would call hybrid materials. In this case, I'm defining hybrid materials as compounds with direct copper nitrogen bonds. And then we see some situations like here in red where we're just reprecipitating some of our ammonium iodide salts as we allow the anti-solvent to be used. So if we look a little bit more closely at the types of compounds that we're seeing, the perovskites sort of look like this. I call them perovskites because they're not perovskites. And as we get further, they get further away from anything that should be defined as a perovskite. Sometimes we have oxygen, sometimes we don't. So they're pretty diverse. So this is what we see, and you see this sort of distortion that you would expect with copper 2+. These are some of the hybrid phases that we observed, and they look far different, right? And so there's more variability in those phases. If we look back at our system, looking at the crystallization field, there's a lot that we can use or that we can understand from these systems with our own intuition. First, the perovskitoids, when observed, exist under real high copper chloride concentrations. The ammonium iodide products exist under low, which is just a reflection of the relative copper and chloride concentration in solution. The copper-free compounds dominate crystallization under copper-deficient conditions. The distinction between our hybrid phases and the perovskitoids almost certainly comes down to the ammonium to chloride ratio, in that they're competing for the coordination site on the copper, and if we have more chloride around, we're much more likely to form materials where we have the copper coordination sites occupied exclusively by chloride as opposed to nitrogens in some of these hybrid type materials. That doesn't explain why we see perovskitoids in these three systems, but not in those. In order to think about that, we had to look at the packing structures of these materials. And if we look, what we see is that hydrogen bonding is, again, important. And with this hydrogen bonding, there's a primary ammonium site that's in a cubic pocket in each of these materials. And the ability of these amines to occupy these cubic pockets is based upon sterics. And so we calculated some geometric steric effect indices, and we see that the sterically less hindered ammonium sites can result in stabilization through hydrogen bonding in cubic pockets and result in the formation of perovskitoid. The sterically more hindered amines can and don't. If we look at the structure of the hybrids, sterics also affect that as well. And so this is sort of our first big circle through our approach, right? We've done 5 systems, lots of structural work, discovered a bunch of new compounds, and we can now articulate some of the hypotheses that govern the formation of these materials. And I would say that it is the copper chloride concentration is really what matters most. Hydrogen bonding is important to stabilize 2-dimensional perovskitoids, and the way in which the hydrogen bonding preferences on these 2D layers work, it's this cubic pocket, which is important. And we need a sterically unhindered primary ammonium site to give rise to that stability, which result in the perovskitoid. And sterics, of course, affect the hybrids as well. So what's the next step, right? So this is the unpublished work in progress. If we have technical hypotheses, we should have our hypotheses. And so the next steps are to decouple copper and chloride and see how that works. In our initial experiments, they were correlated to one another using ammonium iodide salts. Was originally done because of solubility issues. The ammonium chloride salts have a much lower solubility, so we wanted to go with iodide, but going to some of the copper chloride or the ammonium chloride salts should promote the perovskitoid formation more widely. We also need a much bigger set of cations we're working on, and parallel to all of that is we're working to extend these robot-friendly techniques past copper and led to additional 2+ cations. Acknowledgements, and so Josh Dreyer is the computational chemist that I work with a lot. The initial robot work was done with Henry Chan at the Molecular Foundry. Mansour was a postdoc who did a lot of the work, but nearly all of all of the copper work was done by the bottom set of undergrads, a few of which are in graduate school now. Matthias Seller for help with collecting single crystalline diffraction data. The work was funded by DARPA, and I'd like to thank him for attention.